welcome to ML Done. So this is basically the last lecture of the course series, The Birth of Error Functions. And as promised, today we're going to talk about the multi-class classification case, as opposed to the previous case, which was about just a simple binary classification problem. Now, here, what we're dealing with, for a given input to our machine learning algorithm, say an artificial neural network, for instance, we'd like to basically determine whether that input belongs to class 1, class 2, class 3, or class whatever. Okay, and we assume that these classes are mutually exclusive from one another, right? So basically they are independent of each other. So an input can belong to just one of them, right? It can't belong to more than one class at the same time. So these are the assumptions that we have over here, and these are basically the assumptions for a typical classification problem. We of course have cases where an input can belong to different classes at the same time, but that is not the focus of this course. So previously in the binary classification case, we saw that when we want to determine the class of the input, basically we're generating a probability that would tell us the probability of the input belonging to the positive class, and in order to compute the probability for the other class, we would just subtract the generated output from 1, and that way we could see, okay, what is the probability of the input belonging to the negative class. And we saw that in order for our network to generate a probability, a probabilistic value, meaning that for it to have a probability distribution, we would use a squash function, also known as the sigmoid function, which whatever it gets as an input, it would squash it between a value into a value between 0 and 1. So we would see that we can look at it as a probability, and at the same time we are basically, whenever we want to compute the probability of the other class, we would just subtract the value from 1, because again, even in the binary classification problem, the classes are mutually exclusive, right? So an input can belong to either class positive or negative. So the probability of input belonging to either class would be 1, right? So it's a basically general rule of probability. Well, this course is not about probabilities and those basic stuff, but just to give you an idea, just in case you are not basically quite comfortable with this idea. Now imagine that you have a dice, right? And the probability of dice coming up as the value 1, 2, or 6 is 1 over 6, right? That's basically very simple uniform distribution that we have in probability theory. Now the thing is, if I ask you what is the probability of the dice showing up a number, like any number, between 1 to 6, right? 1, 2, 3, 4, whatever. But I just want to know the probability that one of these numbers will come up. Now, if we assume that the dice is fair, the probability would be 1, right? Because we're sure one of them will come up eventually, right? With the same reason, we're sure that the input will belong to one of the classes eventually. So the probability of input belonging to either classes would be 1 in the binary classification problem, and that's also the case for a multi-class classification, as we will see. So enough digression. So what type of output we would need here? Again, we deal with k mutually exclusive classes, right? So basically you can think of this as the input x being an image, right? And the output could be different classes, like one class could be class cat, the other class could be class dog, and the other can be class, I don't know, boat, right? So these classes are mutually exclusive, and the input image X cannot be both cat and dog, or both dog or dog and boat at the same time. Okay, it can be just one of them at a time. Sorry. So for each class, we would generate a value between 0 and 1. By we, I mean our machine learning algorithm, right? So what we would generate first is for class cat, right? So if I ask you, or your machine learning algorithm, what is the probability that X belongs to class cat? Well, before you answer me, I'm basically waiting for you to basically give me a number between 0 and 1, right? Because we're dealing with probabilities. So say you give me 0.2, right? So I want the number, this generated number by your machine learning algorithm, to be a number between 0 and 1 for all the classes, right? So that would tell me what is the probability of X belonging to each one of these classes, right? But of course, only one of them is true. At the same time, not only I want the generated value of the neural network or your machine learning algorithm to be between 0 and 1, can you tell me something? Can I have numbers like this? Point, say, 7 and then point 3. Think about it for a second. Now, this means that I'm telling you that my machine learning algorithm is predicting the class of image X to basically image X to belong to class cat with probability 0.2, belong to class dog with probability 0.7, and belong to class boat with probability 0.3. So think about it for a second. If you have to, just pause the video and think about it. Now, we know that that cannot be true. So if you sum all the possibilities, this exceeds 1, right? So this would be so 10, 12, right? 2, and this will be 1. 1.2. We know that in the theory of probability, the sum of probabilities of all possibilities cannot exceed 1. It has to become exactly 1. Right? So this is the condition that I'm talking about. So we have to make sure that whatever way that we're choosing our neural network or our machine learning algorithm to generate the probabilities for each one of the classes in our experiment, we have to make sure that not only each one of those values is between 0 and 1, but their summation has to be exactly equal to 1. Otherwise, we are not dealing with a probability distribution. We cannot interpret those numbers as probability distribution. Like, for instance, in this case, 0.2, 0.7, 0.3, yeah, they are between 0 and 1, but no, they are not. They don't represent a probability distribution. Okay? And so all of these conditions that we're having here is basically, as I said, forcing the network to generate some values that have a probabilistic interpretation. They have a probability distribution, right? So for binary classification, we had the sigmoid function that would do the job for us, actually. So it would generate the value between 0 and 1, and whenever we want to find the probability for the other class, we would always subtract the generated value from 1, right? So in other words, the summation of the probabilities of the input belonging to either the positive or the negative class is always 1, because we're dictating this to the network. You remember in the binary classification case, if you remember, as a reminder, we said that if the input belongs to class 1, which is this case, we are trying to maximize the likelihood, and likelihood in that case would be y sub I. And if the input belongs to class 0, we are maximizing 1 minus y sub I, right? So this 1 right here, This is important because if I ask you what is the probability of the input belonging to either class 1 or 0, or a positive or negative class, like either one of them, then you would say, okay, the probability that it belongs to class positive, or the case where the ground truth is 1, t sub I equals 1, we know that it is y sub I, right? And the probability that it belongs to class negative, or where the ground truth is 0, is 1 minus y sub I, right? So we have these two probabilistic numbers, these numbers that are between 0 and 1 because of our sigmoid, right? Now if I sum them, as you will see, we get this 1 again, right? So this is exactly the same story that we have in the multi-class classification problem. Let's talk about the appropriate output function that would address our concerns in terms of generating a probability distribution, right? So imagine that you have some artificial neural network or whatever, say some sort of machine learning algorithm here. That's not our concern here, okay? We're not focused on that. And we have the input vector over here, right? It just gets into your machine learning algorithm. So let's consider this guy over here as a black box, right? We don't care about what is inside in this course, okay? So what it does is it generates some values, z1, z2, and z3, right? Because in this case, we are considering the case where we have 3 classes, right? So we want our network to generate 3 values for us. But get this, neither one of these values, z1, z2, and z3, are probabilistic. I mean, they're not probabilities. They can have any range, any values, right? So they have to go through some function over here. Each one of them has to go through a function so that that function would crush them, right? Would crush them in a way that the generated values, which are y sub 1, y sub 2, and y sub 3, not only are between 0 and 1, but their summation would be also 1, right? So the question is, what is this mystery function? That is what I mean by the output function, right? So remember, we have 2 conditions here. Number 1, we want y sub 1, y sub 2, y sub 3, all of them to be between 0 and 1, so that they would represent probabilities. And our second constraint is that we'd like the summation of all the outputs of our network, all these probabilities, to be 1. Otherwise, they cannot be probabilities, right? So whatever this mysterious function is, the input to this function would be these z's, z of 1, z of 2, and z of 3. And then the output would be y sub 1, y sub 2, and y sub 3, which would satisfy this condition, both of these conditions, right? So I'm going to focus on only one of them just to simplify the case. Let's talk about y sub 1. The function that we're talking about has a name, and its name is the softmax function. It's a very interesting function, actually. Let's take a look at it. So let's see how it will generate y sub 1 for us, and then y sub 2, then y sub 3, right? But just to simplify the case, let's just focus on y sub 1, for example. The way it works is that, let me just write the first general formula. Y sub I equals e to the power z of I divided by the summation of e to the power all the z's, all the z's where j goes from 1 to k, and k is the number of our classes, right? In this case, k is 3, right? So k is 3. Now, let's see how this would compute, say, y sub 1. The way this works, and then you can generalize this to y sub 2 and y sub 3. Actually, this is quite simple. For y sub 1, the way it works is it only gets the z of I, right? It only considers what is received over here from your black box artificial neural network, okay? So it would just say, okay, I'm going to take that value, whatever it is, and raise it, use it as a power to my exponential value, right? So z of I. So in this case, I is 1, right? And then I would sum all the other, the e to the power of all the other z's, including z of 1. This is very important. So we would have e to the power z of 1 plus e to the power z of 2 plus e to the power z of 3. Now, you can see actually here that, first of all these values, e to the power, all of these values, is a positive value. And what is even more important here is that this value is always between 0 and 1. Y sub 1 is always between 0 and 1 because the denominator over here is always smaller than the denominator. Because of that, the highest that y sub 1 can ever get is 1, right? And that's when the prediction of your network is spot on, okay? But what is important to notice here is that this y sub 1 is always between 0 and 1, okay? And one more thing about the summation of all these y values. What I'd like to do here is to actually basically erase this whole board and walk you through the whole thing and show you that the summation would actually be will actually be 1, and as a result the softmax function, the way it manipulates all these z values, not only those y values will be between 0 and 1, but the second condition is also satisfied, where the summation of all these y values is indeed value 1. So let's see. So y sub 1, we already did that. So y sub 1 equals e to the power z of 1 divided by e to the power z1 plus e to the power z2 plus e to the power z3, right? Now if I were to ask you what's the output of the softmax function for the second output unit, you know that what it gets, what the softmax function gets for the second output unit is z2, right? That's all it gets here. But remember that it also considers other z's, right? It doesn't just look at z2, it also considers z1 and z3, and that is very important. That's a tricky part about the softmax function. So it would just use e to the power z of 2 in the denominator, and then it would just consider all the other z values and would have them in the denominator, right? And same story about y of 3. So e to the power z of 3 divided by z1 plus e to the power z2 plus e to the power z3, right? So we can see that each one of these values are between 0 and 1, right? Because for each one of these, the denominator is smaller than the denominator, right? So the first condition is satisfied. So each one of them has a potential to be a probability value. Now let's see if the summation of all these apparently probability values would be 1 or not, right? So let's just sum them. So y sub 1 plus y sub 2 plus y sub 3. So if we sum all of these, we have a common denominator here, z2 plus e to the power z3, and then the nominator for the whole thing would be e to the power z1 again plus e to the power z2 plus e to the power z3. So it's just very straightforward math here, and just 1, right? So again, the second condition is satisfied here. Remember, the whole secret of the softmax function being able to satisfy this condition is because, as you see, even though I'm computing y sub 1, I'm considering all the other z's in the denominator, in the denominator, right? So basically, it's only by considering everybody else that I can be sure that the summation of all the outputs would be equal to 1. It's a little bit too much into detail, but I'm going to cover this whole softmax, sigmoid, and the math behind it in terms of the backpropagation and the actual learning algorithm, and why we have these exponential values over here. I'm going to dig into details of these in some other course, but for now, let's just say that the softmax function can generate a probability distribution for us, which is all we are after. Now, as a reminder, for the binary classification problem, when we were trying to come up with a nice assumption on the likelihood, right? So again, the likelihood of observing t's of I given the observation d's of I and the w, which is the parameters of your network, or the weights, say, for instance, in your neural network. We said that, okay, we can model this with the Bernoulli distribution, right? And this has a good characteristic. So when the values of the ground truth is 1, meaning that the input d's of I belongs to the positive class, we can see that the only surviving value of this whole of this whole expression would be y sub I, and when t sub I is 0, the only surviving element of this whole thing would be 1 minus y sub 1, right? Y sub I. So we would have either this or this, right? But in both cases, remember, we're trying to maximize the likelihoods, right? That is maximum likelihood estimation, right? So if the ground truth is 1, we're trying to maximize y sub I, meaning that let's maximize the output of our network. Remember, y sub I has been generated using the sigmoid function, and we know that it is between 0 and 1, okay? And if the ground truth was 0, we said that we're trying to maximize 1 minus y sub I, and we said that maximizing 1 minus y sub I means minimizing y sub I, all right? So as y sub I gets smaller, 1 minus y sub I becomes bigger and bigger. And that is how you maximize that. And in other words, making y sub I smaller and smaller so that it would get as close as possible to the ground truth, which is 0, right? So we said that we can just model this by Bernoulli distribution, as simple as that, as you can see over here, right? So we have the same story actually over here for the multi-class classification problem. Now imagine that, again, the same story, the likelihood of d's of I and w belonging to class I, which we represent by the ground truth, okay, t's of I. So again, what we want this, whatever this likelihood distribution is, what we want is that we'd like that if the ground truth is 1, so t sub 1 is 1, meaning that d sub I belongs to class 1, right? Then we'd like the distribution to have the value of y sub 1. And if t sub 2 has been turned on, meaning that the ground truth for the second class is 1, we'd like the network to, with the likelihood to represent only y sub 2, right? Which would be the desired output of your network that you'd like to be as close as possible to the ground truth. And also for t's of k being equal to 1. So if the input belongs to the kth class, you only want to consider y's of k, which is the kth output of your network, okay? Remember, so let me jump here for a second. So you have your black box machine learning algorithm. It would generate z of 1, z of 2, and z of 3, and which means that we have 3 classes here. Using softmax function, we generate these values, y's of 1, y's of 2, and y's of 3, that are probabilistic values. They're between 0 and 1, and they sum to 1, right? Now, let me just give you an example of what I mean. So we can have, say, for class 1, we can have probability 0.2. For class 2, we can have probability 0.7, and I don't even need to spell this out for you anymore, but you know that this has to be 0.1, okay? So that the sum would be 1. Right, now let's say that we know, this is very important, let's say that, so these are the predictions of your network, right? It means that I believe X belongs to the class 1 with probability 0.2, belongs to class 2 with probability 0.7, and it belongs to class 3 with probability 0.1, right? Now let's say that we know actually X belongs to class 1, right? But your algorithm is kind of determined much more than the other cases that the input belongs to the class 2 because it has higher probability for it. It has generated higher probability for it, right? Now, if we know that the input belongs to to class 1, actually, the way we would represent this to the network, remember, this is very important. How would you represent the truth to your machine learning algorithm, right? The way they would do that is they would just represent 1 over here for the true class, right? For the class that we know that X belongs to. Say, for instance, in this case, we know that X belongs to class 1. So we would put a 1 over there, and we would put zeros over here, right? In the case of the likelihood, right? So the probability, basically the probability of observing T given Y, right? So that is my likelihood. Remember, this is very important. So this is Y of 1, Y's of 2, Y's of 3, right? I know that the true class is class 1, right? So what do I want to maximize here? Which one of these Y's do I want to maximize here? This is very important. Please pay like 110% attention. Of course, I want to maximize Y's of 1, right? Now it is horrible. Now it's 0.2. We're far away from the truth. So I want to maximize Y's of 1. So if I know that the truth is actually class 1, the true label of the class is class 1, right? I want to basically maximize Y's of 1. So I want to maximize the likelihood of observing this vector, right? 1, 0, 0. Let me just break this guy down here for you. So T and Y are basically vectors, right? It basically means observing, the probability of observing one, very unconventional of me to write this like this, but this is more visual. The probability of observing T, which is basically nothing but a vector, given the output of my network, which are in this case 0.2, 0.7, 0.1, right? So since I know, so this is Y's of 1 over here, this is Y's of 2, this is Y's of 3, right? And this is T's of 1, this is T's of 2, this is T's of 3, right? So I know that T's of 1 is the truth, which means that the input belongs to class 1, right? So in this case, This is the likelihood, isn't it? And I want to maximize it, right? So if I want to maximize it, which this means that I want to maximize one of these outputs, one of these y's. Which one would it be? Obviously, that would be y sub 1, right? So if, say, class 2 was the truth, meaning that basically we had a 0 here and we had 1 here, right? Sorry for the scribble, but I just want to make a fast point here. So if 0 was here and 1 was here, meaning that class 2 was actually the truth, then we would only consider y sub 2, and we would so we want to maximize y sub 2 over here, right? So that is the whole story behind this likelihood story over here. So given t1 being 1, I want this likelihood to have the value y sub 1. Then I want to maximize y sub 1, right? And the same story down there. So the way you can represent this whole thing, this whole section over here, is through this guy. Now, this has a name. This distribution has a name, and it's called the multi-nomial distribution. Just as in the binary classification that we named this distribution over here as the Bernoulli distribution, right? So this guy right here has a name, and it's called the multinomial distribution. Now, just to give you some sort of a small proof, so let's say the likelihood of DMW, right? Let's say that I know that the input belongs to class 1, right? So here in this notation, input is D, right? If I want to generate, basically use this formula and basically follow the formula that I've just come up with. So this means that I equal to 1 to k, which is the number of classes from y sub I to the power t sub I, right? So let's say we have 3 classes, right? So this means y sub I to the power, let's start from 1. Y sub 1 to the power t sub 1 multiplied by y sub 2 to the power t sub 2 multiplied by y sub 3 to the power t sub 3, right? But wait a second. If I know that the input belongs to class 1, then it means that only t sub 1 has the value 1, and t sub 2 and t sub 3 are 0, right? Remember, this, as I said here, this is how you represent the truth through your algorithm, right? 1 for the true class and 0 for the other classes, right? So by the same logic, if class 1 is a true class, I know that t sub 2 and t sub 3 are 0, right? So then this would mean y sub 1 to the power 1, y sub 2 to the power 0, and y sub 3 to the power 0. So this is 1, this is 1. So the likelihood of t sub 1 basically being equal to 1, given the input and the parameters of your network. You want to maximize this likelihood. Basically, you want to maximize y sub 1, okay? So as you can see, this multinomial distribution can generate exactly what we've described here, right? So given the ground truth, the ground truth that we are considering as the true label for the true class label for the input, we want to maximize the corresponding y sub I, which is the output of the network, which is also the probability that the network thinks that the input belongs to class I. So then again, if the network has generated values like 0.2, say 3, and 0.5, and if you know that the ground truth is actually class 3, then you must put 1 here, and then 0 here, 0 here, right? And the corresponding likelihood for this whole case, if I want to compute this, it would be, again, based on the formula that we talked about, I equals 1 to 3 y sub I to the power t sub I, right? And if I want to break it down over here, this would mean y sub 1 to the power t sub 1 multiplied by y sub 2 to the power t sub 2 and y sub 3 to the power t sub 3. So y sub 1 is 0.2. T sub 1 over here, so wait, this is t sub 1, this is t sub 2, this is t sub 3, right? For class 1, class 2, and class 3. So t sub 1 is 0. Y sub 2 is 0.3. So remember, we have multiplication here. And the ground truth for that, t sub 2 is 0, and again multiplied by 0.5, which is y sub 3, and then t sub 3 is 1, right? So what we get here is 0.5, right? So basically, what does it mean? It means, according to our network, according to this black box over here, the likelihood of observing class 3, right, means that T3 being equal to 1. The probability of observing T3 being equal to 1 given our inputs, or sorry, in this case, I just want to be more consistent. I have to be more consistent basically with my notation. My apologies. So anyways, the input x and the parameters of the network inside, right, based on these values, this is equal to 0.5. Remember, we know that the ground truth is telling us that x belongs to class 3, but what your machine learning algorithm is producing here is 0.5, right? So it is horrible. So what do we do then? We will try to tweak our machine learning algorithm in a way that for the next inputs that are similar to this guy, to this x that we have over here, it would generate higher and higher values for y sub 3, right? So it would generate higher and higher probabilities of those inputs belonging to class 3. Okay, but I don't want to jump into details of that. That's another course on its own. It actually deserves another course on its own. But that's a whole philosophy of learning. We tweak the model, meaning that we learn the parameters inside the model. Okay, we make these parameters, in this case these w's, better and better and better, meaning that we would make sure that we would maximize the likelihood of observing the ground truth. Okay, which means that we'll try to make the y's, this is all the y's, y sub 1, y sub 2, y sub 3, y sub k, okay, as similar as possible to the ground truth. Okay, so we want to basically be as accurate as possible. So from this point on, it's actually quite easy. So as we said, the likelihood is we show that like according to this formula, this multi-nomial distribution, right? And so we want to apply the log of likelihoods, right? So if you remember, we said that we are assuming, not assuming, we basically underwent loads of mathematical derivations to get to this place. If you remember, we said that error, according to maximum likelihood estimation, is minus the log of the likelihood of observing the ground truth given the output of our network, right? So we have to take the log of both sides, right, to generate this error function. So the log of the likelihood here is the log of this whole thing, right? I goes from 1 to k, oops, y sub I to the power t sub I, right? And we know that, we've seen this before, that the log of a multiplication can break down into a sum, right? You can write this as log of A plus log of B. We've seen this multiple times actually. So I can turn the multiplication into a sum. Again, I from 1 to k. The log goes in, right? Log of y sub I to the power t sub I. Remember, this whole thing is inside the log, okay? And we know that log of a to the power b is equal to b to multiplied by the log of a, right? These are simple logarithmic formulae that we've used a lot actually to this time. So then this would mean that the sigma stays the same and t sub I goes to the side, right? Goes becomes the coefficient. So t sub I comes here and we have the log of y sub I. Again, I goes from y to k, right? Now, so we can stop over here. So this is the log of likelihood, right? And we know that the error function is minus the log of likelihood, right? So basically, let me make it more colorful because this is what we've been waiting for. So the error is, okay, sorry, I have to change the thickness a little bit. Okay, so the error equals minus the log of likelihood, and that is error equals minus the sum of t sub I multiplied by the log of the outputs of the network for I going from 1 to k. And this, my friends, is the error function that you can use for a multi-class classification problem. And that has a name actually. Let me erase this bit and write the name over here. The name of this error function is the cross-entropy error function. Okay, so we can actually kind of play with this one. Let's see if I can do it over here, right? Or maybe, let's see. Right, so I had to erase this so that we could be more clear on this. Now, again, the same example, right? So these are the y's, the predictions, the probabilities, and these are the ground truths, right? Now, let's compute the error, right? So how would the error work again? Let's just remind ourselves. So error is minus, we have a sum, I goes from 1 to k, in this case k is 3 because we have 3 classes, and we have t sub I log of y sub I, right? So let's just follow the formula. Let's see what it would get us. A minus, then we have a sum, right? So t sub 1 log of y sub 1 plus t sub 2 log of y sub 2 plus t sub 3 log of y sub 3, right? Now, you can see where I'm going with this, right? So t1 is 0, so this term cancels out. t2 is 0, this term cancels out. t3 is 1, right? So this whole thing reduces to minus, and this guy over here, we know that it's 1, so I don't even need to write that, so that would be log of y sub 3, right? This would be the error. What does this really mean? So this would be minus the log of y sub 3, which is 0.5. This means if my ground truth vector is 0, 0, 1, which is to say that the input belongs to class 3 and not class 1 or not even to class 2, just class 3, okay? And if the prediction of my network is 0.2, 0.3, 0.5 for class 1, class 2, and class 3 respectively, then it means that the error in my prediction is equal to minus the log of 0.5, right? That is the cross-entropy error function. What does it really mean? It's a measure of measuring the distance between your predictions actually and the ground truth. So cross-entropy is nothing but a distance measure. Okay. Remember that, for example, if y sub I is 1, right? So let's say in this case, for example, let's say that the network has actually produced, let's just change it. Let's just say that the network has actually produced 1 here, okay? So then this would mean that y3 we can put 1 over here, right? And log of 1 is 0, so the error would be equal to 0. It means that we are right, spot on. Okay? It means that there is nothing wrong with your predictions, because as you know, if this is 1, then this would mean that y2 should be 0 and y1 has to be 0, because the sum, as we said, has to be 1, right? So as you can see, the vector y is 0, 0, 1 and the vector ground truth is 0, 0, 1, right? So the two vectors are exactly the same. Because of that, the error, the cross-entropy error, will give you 0, because it's basically saying that there is no distance between your prediction and the ground truth. They're exactly identical. Lovely. Now, so some neural assumptions for the multiclass classification case. So we argue that the proper output function for the neural network, for your neural network machine learning algorithm, is a softmax function, okay? And we also argued that if we assume that the likelihood is distributed multinomially, then the associated likelihood, basically the associated likelihood is so similar, basically identical to the famous cross-entropy error function, right? So, as I said, that error function that we just got has a name, and it's been around even before the multi-class classification case. It has a name, and that's why I put it right here, that it really looks like, okay? So it's quite amazing how things mathematically work out. The error, again, is my sigma over here minus the log, and we have the ground truth here, and we have y sub I here, and I goes from 1 to k. So this has a name. And if you remember, in the binary classification case, we had the binary cross-entropy error function, right? So it's just very interesting. So we had t sub I log of y sub I, and then we had 1 minus t sub I, then the log of 1 minus y sub I. I'm not quite sure about these negative signs over here, here, and here, but that's not my point. My point is, this is the binary cross-entropy function, and the one that we just got over here is the general cross-entropy function. Okay? Just wanted you to basically see the similarities between the two. They're actually very, very similar. but please forgive me on not remembering these signs over here, but I'm kind of sure that, I'm nearly sure that that's the case, but just don't take my word for it. Just make sure that you actually go to the previous lectures and do a comparison between the cross-entropy function and the binary cross-entropy function, and you can see there are very similarities over there. Oh, that was great. That was really, really great, and we basically finished it. We talked about the multi-class classification problem, and we wrapped the course at the birth of error functions. We talked about the Bayes rule in this course. We talked about the likelihood and posteriors, and we showed how you can use likelihood to basically come up with a good logical definition of an error function. Then we talked about different applications such as regression, where we showed that you can have a linear unit. Actually, you should have a linear unit. That's a logical case over there. And with that, you can pair it with the sum squared error function for the case of regression. And we showed that for multi-class classification problem, you can use softmax amplitude function, and you would have the cross-entropy error function, and we proved that. And also for the case of binary classification problem, we showed that sigmoid and the binary cross-entropy function would go well together, and we showed that we kind of proved actually that how the binary cross-entropy function has come to being. So in this whole course, we basically showed you how these error functions came into being, and hopefully in the next courses in ML-Done, especially backward pass and forward pass from scratch, we'll focus more and more into the learning process and how these pairs of outputs and error functions affect the very learning process. It was a pleasure teaching this course to you, and I do hope that you've actually benefited from it and you've learned what you had intended to learn, and hopefully even more. So on behalf of ML-Done, take care of yourselves, and I hope that I will see you in our other courses. Take care, and bye.